My name is Paweł Gora. I'm a researcher from the University of Warsaw, Faculty of Math and Computer Science. And I'm also founder and leader of Warsaw Quantum Computing Group. And today I will tell you about quantum computing, indeed. I will give you an introduction to quantum computing. There will be a bit or a qubit of theory behind quantum computing. I will tell you about gate-based quantum computers and so-called adiabatic quantum computers. And then I will present some possible future applications of quantum computers. And finally, I will share with you my experience with building quantum computing awareness and quantum computing community in Poland. All right, so let's start. I guess that many of you studied computer science and learned about algorithms, which are just mathematical concepts. But when we implement algorithms and run them on our computers, they are run in our physical world, which is quantum. So the computing is also quantum, governed by rules. The computations are governed by rules of the physical world. I'm not sure how many of you are familiar with quantum mechanics, but maybe just to recall, there is famous postulate from Max Planck that the electromagnetic energy could be emitted only in quantized form. So for example, the energy of electromagnetic wave is equal to Planck's constant multiplied by frequency of electromagnetic wave. And this is the minimum portion of energy that can be emitted. So we cannot emit a small amount of energy as we want, a smaller amount of energy. And also, in case of computations, there is also famous Landauer principle, which says that there is a minimum possible amount of energy required to any logically irreversible manipulation of information, such as erase one bit of information. So, okay, we can run computations, but we should be aware that we do it in a physical world, which has some limitations. More than 50 years ago, Richard Feynman, in his famous book, There's Plenty of Room at the Bottom, said that there's nothing that I can see in the physical laws that says the computer elements cannot be made enormously smaller than they are now. In fact, there may be certain advantages. So a bit later, Gordon Moore formulated his law that the number of transistors in a dense integrated circuit doubles about every 2 years. And this prediction proved accurate for several decades. It has been used in the semiconductor industry to guide long-term planning and to set targets for research and development. Recently, we can observe that the Moore's law is dying. So even Moore in 2015 said that I see Moore's law dying here in the next decade or so. And for example, the Intel company observed that the pace of advancement has slowed. So this density doubles not once per 2 years, but once per 2.5 years. 2 years later, they also stated that the trend will continue thanks to a new technology which is called hyperscaling. But we cannot do it infinitely, right? Because if the trend has to be continued, then in about 2035 or 2040, the size of a single transistor should be the size of one atom. And there we have different laws. We have laws of quantum mechanics, which implies that computation should be done in a different way. All right, so how can we do computations in such a small scale? And again, let's cite Richard Feynman. Now we can, in principle, make a computing device in which the numbers are represented by a row of atoms, with each atom in either of the two states, so 0 or 1. That's our input. The Hamiltonians start Hamiltonianizing the wave function. The ones move around, the zeros move around. Finally, along a particular bunch of atoms, ones and zeros occur that represent the answer, the solution. Nothing could be made smaller, nothing could be more elegant. No losses, no uncertainties, no averaging. But can we do it? That's the important question. And as you may expect, we already know the answer, at least partially, because we are already able to build some relatively small quantum computers, but they are quantum computers. On this image, you can see a quantum computing processor from Google called Bristlecone, which has 72 qubits. On the right side, you can see the design of the device, so connections of qubits. Okay, so what's the difference between quantum computers and classical computers? So as you know, in classical computers we have bits and classical gates. In quantum computers we have so-called qubits and quantum gates. So as you know, in case of bit we have a state which may have two possible values, 0 or 1. So mathematically it's very simple. It's just element. The state is just element from the set 0 and 1. In case of qubit, it's much more complicated. The state may be in a superposition of state 0 and 1. So we don't have 0 or 1, but the state is something in between. But it's also not only just a real number between 0 and 1, but it's something more complicated because mathematically it's a unitary vector of the two-dimensional Hilbert space over complex numbers. So it's quite complicated. Okay, in case of classical computers, the state is determined, it's deterministic. So we can know every time, we can know exactly whether the state is 0 or 1, and the state can be changed from 0 to 1 and vice versa. In case of quantum computers, since the state is something between 0 and 1, and we don't know exactly, so to get values 0 and 1, we can do a measurement which breaks this superposition. So after the measurement, the state is determined again, so it's 0 or 1, and the superposition is broken, but we just have a certain probability of getting 0 or 1 in the measurement. And the probability depends on the qubit. And our quantum gates can just modify the probability, modify a quantum state and modify probability of getting 0 or 1 in the measurement. So that's the idea. All right, so we can represent our quantum state as a superposition of two basic pure states, 0 and 1. So these 0 and 1 are our pure states. I said about this Hilbert space, so we can say that it's in orthonormal base of a quantum system. A and B are complex numbers, and squares of their amplitudes are probabilities of getting 0 or 1 in a measurement. So multiplying those values A and B by a unitary vector doesn't change the quantum states, so A and B can be transformed to polar coordinates. So the quantum state can be represented on something that is called Bloch sphere, and we can represent a quantum state as just a point on such a Bloch sphere. And some people say that quantum computing is just a journey on a Bloch sphere. So I said that quantum gates, when we run computations, we just transform one point on this sphere to another point on this sphere. So on one antipode we have state 0, on the second antipode we have state 1, and the probability of getting 0 or 1 in the measurement just depends on proximity of our state to those antipodes, 0, 0, or 1. And our computations, our quantum gates can just change our position of our quantum state on this sphere. So that's the idea. And why it is important? So in case of classical computers, on n bits we can process only one n-bit number at the same time, right? In case of quantum computers, using n qubits, we can process all 2 to the power of n-bit numbers at the same time. That is called quantum parallelism. So you can see here a relatively simple circuit, quantum circuit, in which initially we have n states 0, pure state 0. We apply so-called Hadamard gate. So this is this H letter. I will tell about it later. And then our n states are in a superposition. And we can prepare a superposition of 2 to the power of n numbers. So we have all possible states, right? We have n qubits. On every qubit we may have 0 and 1 in the measurement. So in total we may have 2 to the power of n possible states. And we can process all of these states at the same time. So if we apply some other quantum gates, we can apply those quantum gates in fact to all states at the same time. Another thing why it's important is the stochasticity. So in case of classical computers, our results are deterministic, and randomness is in fact a pseudo-randomness. in case of quantum computers, we may have real randomness, and we can easily sample from probability distributions which are difficult for classical computers, such as Boltzmann distribution, for example. I already told you about Hadamard gate. So in fact, that's the gate which is used to just create a superposition of state 0 and 1. So when we have a pure state 0, when we apply the Hadamard gate, we just get quantum state 0 plus 1 divided by square of 2. And after doing a measurement, the probability of getting 0 and 1 is just half. So probability is equal for 0, 0, and 1. So there are also some other interesting gates. So for example, Pauli gate, which we can consider as a negation. Pauli Z gate, 0 just is still 0, but 1 becomes -1. There might be also gates which takes 2 inputs. For example, C0, it's a very important gate. We have 2 qubits, and 1 qubit is a controller for NOT operation on the second qubit. So just to show you an example of relatively simple quantum circuit. So initially we have 8 qubits, in analogy to 8 bits in our classical computers, and we can apply our quantum gates. In case of this circuit, we can get a quantum state such that with probability half, with 0.5, we can get the ASCII code which represents the letter P, and also with the same probability we can get the ASCII code which represents the letter G, so my initials. So it's relatively simple because in case of qubit number 7 and 5, the state is the same, so it's 0. In case of state qubit 6, we apply this Pauli X gate, which is negation, so the state becomes 1. In case of qubit number 4, we just apply the Hadamard gate, which makes superposition. So we can get 0 or 1 with probability 1/2. And based on the value of this qubit, we can also get different results of measurements of qubits and positions 0, 1, and 2. That's relatively simple quantum circuit. So you can see that in case of classical computers, on 8 qubits, on 8 bits, we can just represent one 8-bit number. In case of quantum computer, on 8 qubits, we can represent potentially many 8-bit numbers at the same time. What are applications of such computations? One of most interesting and important is quantum cryptography. Potentially, we can break some classical cryptography algorithms. For example, the algorithms which are based on the difficulty of the factorization problem. So I will tell you a bit more about it on the next slide. Also, solving combinatorial optimization problems, which may have applications in transport, logistics, or AI machine learning. So I will also tell about it later. Sampling from difficult distributions. Yes, so thanks to this non-deterministic states and real, true randomness. Simulating quantum processes, which may help in discovering new materials, new drugs, for example. Right? So in case of factorization, you know that the problem of multiplying 2 n-digit numbers is relatively simple, so we can do it in n log n. But if you want to factor n-digit number, it becomes difficult. So no algorithm has been published that can factor on all integers in polynomial time. But we don't know yet whether such algorithm exists or not. It hasn't been proved yet. It's generally suspected that such algorithms do not exist, and the problem is not in class P, so we cannot do it in polynomial time. But it hasn't been proved. The best published algorithm is based on so-called general number field sieve, but it's still exponential time of computation. So we don't know any polynomial algorithm for this problem in case of classical computers, and it's generally believed that no such algorithm exists, so it will be quantum supremacy, because in case of quantum computers, we know such algorithm. It's so-called Shor's factorization algorithm. So you can see that the time of computations is polynomial indeed, and in fact it's a hybrid algorithm. So some part of computations are run on classical computers, but there is a quantum subroutine which is responsible for finding a period of a long sequence using so-called inverse quantum Fourier transform. So I'm not going into details here, but I recommend you to read about this algorithm because it's very interesting. Another application and also a bit different approach to doing quantum computations is so-called quantum annealing. So quantum annealing is a process or algorithm which can be run on so-called adiabatic quantum computers. So the idea is that first we should represent our optimization problem as a so-called E-sync model to which we define Hamiltonian. And I will tell on the next slide what is exactly the Hamiltonian of a given physical system. Initially we prepare a basic quantum state in which, for example, all possible solutions are in a superposition. So, for example, we have 2 to the power of n possible solutions, right? And every solution is equally probable. For a parameter is equal to 0, that's our initial state. But then when we modify the value of s from 0 to 1, then our function also changes and we get this icing model corresponding to our problem. So, the idea is that for the given Hamiltonian, our quantum or our state or our system, our physical system, should be in a state with minimum energy for the whole time. So when we change the value of s, we should be still in the minimum, right? And in practice, if we do such changes of the value as slow enough, so the final state should be solution of our problem, so should be a global optimum. In reality, it's difficult to do it slow enough, but even if we do it faster, then it's still quite possible that even if we don't get a global solution, then we can get a quite good solution, approximately correct, heuristically optimal solution, right? So in practice, we can change the value of this S parameter by modifying a strength of a magnetic field. So that's the idea. All right, so now some equations, but I will not go into details here, so don't worry. I just wanted to explain what's the Hamiltonian. So the Hamiltonian is just a mathematical description of some physical systems in terms of its energies. So, and the whole idea of quantum annealing is to transform or represent our problem as a Hamiltonian of some physical system, which we also represent on our quantum computer, right? And when we run computations, we still, if we ensure that we are still in the minimum of the system, in the state with minimal energy, then after finishing computations, we should be close to global minimum. So that's the idea, basically. And the whole thing is possible thanks to the process called quantum tunneling. Initially, when we have this simple Hamiltonian, then we have some basic solution. But then when we change value of our parameter s, so we change the strength of a magnetic field, then we can just also change the landscape of our Hamiltonian. We change the landscape of our function. And as I said, the nature always tends to keep the state of the system in a state with minimum possible energy. So that's why, thanks to the process of quantum tunneling, in quantum mechanics it's possible to just jump from one local minimum to another local minimum, which is lower. So it's something that is not possible, or it's not easy to be done on classical computers using, for example, gradient descent or some other optimization techniques. So that's the advantage of quantum computers and quantum annealing. All right, and this quantum annealing algorithm may have some applications, and it's not science fiction anymore because there are some real applications already. For example, Volkswagen together with D-Wave company. D-Wave is a company from Canada which is one of producers of so-called adiabatic quantum computers on which we can run this quantum annealing algorithm. 2 years ago, they published a very interesting paper in which they show how to use this quantum annealing algorithm to optimize traffic flow. So initially, they built a road network It was a road network of Beijing in China, and they have routes from real GPS data. It's called T-Drive data sets from taxis in Beijing. So there were taxis traveling from the city center to the airport, so they knew the routes of taxis, of course. But for each taxi, for each car, they added 2 possible routes between source and the destination. They also assumed that travel time is proportional to the square of a number of cars on a route, on a given road segment, which is a simplification. So in reality, it's not true that this relation is quadratic. But that's the only assumption in which they were able to solve this problem easily on quantum computer. And the goal was to minimize the total travel time, right? So initially, so first we introduce a condition which just says that every car should take exactly 1 route, right? So Q, I, J is 0 or 1, depending whether car I takes route J. And yeah, so the first condition just indicates that every car should just take exactly one route. And then for every road segment, we calculate the cost. And as I said, we assume that the cost is just a square of number of cars passing given road segment. And then we have our objective function, which we want to minimize. We want to minimize our cost, right? So we sum up costs of over all road segments, and we also add this condition. And if we just set the value of parameter lambda high enough, then we can be sure that in case of our optimum of our objective function in our minimum, this first condition will be fulfilled, right? So every car will just take a single route. All right. So we have a function to optimize, and we can observe that it's a quadratic function with many variables, and we can transform it to so-called quadratic unconstrained binary optimization form, QBO, right? So there exists a matrix Q which helps us represent our problem in such a way. And given this matrix, finding assignment which minimizes our objective function is equivalent to minimizing an Ising model, and that is NP-hard problem. So we cannot do that on classical computers accurately in polynomial time. At least we don't know how to do it at the moment. But it can be solved using quantum annealing on D-wave, on this adiabatic quantum computer. In experiments, they had 418 cars and more than 1,254 logical variables. So the size of the space of possible solutions was astronomical, as you can see. So we cannot just test every possible solution on classical computer. Then they ran computations for 22 seconds, and as a result, they achieved a relatively small number of streets that were heavily occupied. So that was the initial traffic congestion or travel times in this setting, and after running experiments, they achieved much better traffic assignment. So of course, it's just simplification because they assume that there are no other cars on the road, right? So they had to do many simplifications, but thanks to that, also the solution is relatively simple, and I was able to show it and explain it to you. All right, there might be also some other applications of this quantum annealing approach. So for example, in solving traveling salesman problem and similar NP-hard problems in logistics, such as vehicle routing problem and pickup and delivery problem, I can tell you that recently my research team at the University of Warsaw has developed new algorithms, new solvers based on quantum annealing, which outperformed all previously known approaches to solving vehicle routing problem on quantum computers. So classical computers are still better at the moment, but in case of quantum computing, we can do it better and better. And there are already logistic companies interested in such solutions. All right. So maybe I should also explain that in case of traveling salesman problem, the goal is to just visit every customer or every point in our network, in our graph, with a minimum cost, right? So we have one vehicle, and we are interested in finding the optimal order of visiting points or our customers. In case of vehicle routing problem, we may have just many vehicles. We may also have time windows, for example, or limited capacities. All right, there might be also applications in artificial intelligence, and for most of existing machine learning algorithms, there are already quantum counterparts published in the literature, yeah, people just publish better and better papers and algorithms. So the whole domain is growing, and we know, so at least from a theoretical point of view, we already know quite a lot about such algorithms. The problem is that we still don't have quantum computers, which should be large enough to give us advantage. But just to explain you, for example, how this quantum annealing algorithm can be used, I told you that it may have fine applications in solving combinatorial optimization problems. And in fact, in machine learning, many problems are in fact optimization problems, and in many cases they are combinatorial discrete optimization problems. So for example, in ensemble learning, we have many models, and we just need to find values of parameters or weights which we should use to add or combine results of many different models, right? And then finding optimal setting of such parameters is a combinatorial optimization problem. So also training neural networks is optimization problem. It's not combinatorial. It's rather continuous optimization. But potentially we can also think about such quantum algorithms. All right. Yeah. So I said that the problem with such algorithms is that at the moment they are not available quantum computers that will be large enough to do it. So the state of the art in case of gate-based quantum computers is 72 qubits. As far as I know, it's a quantum computer built by Google. The Rigetti company, which is a startup from Silicon Valley, announced that last year they announced that they expect to have a quantum computer with 128 qubits this year. As far as I know, it hasn't been announced yet, but we are still waiting. And D-Wave company, which built this adiabatic quantum computers, announced that they next year they will build the next adiabatic quantum computer, which is called Pegasus, with more than 5,000 qubits and totally new topology of connections between qubits. So in last few years, there is quite good progress in development of greater and bigger quantum computers. Besides quantum computers, beside the hardware, we also already have software development kits for developing programs which can be run on quantum computers. They can be run on quantum computers or also as a simulation on classical computers in hybrid settings. So for example, there's Qiskit from IBM, Forest from Rigetti, Strawberry Fields or Pennylane from Xanadu. So the Pennylane is considered to be so-called TensorFlow of quantum computing. So it's possible to do automatic differentiation, quantum differentiation on quantum computers. D-Wave Sleep for running this quantum annealing algorithm. So right now it's possible to get free computational power. There are also SDKs which are based only on simulators of quantum computers. For example, there's Microsoft's quantum development kit with Q# language, similar to C#, and you can also write code in Visual Studio, for example. All right, so at the moment it's hard to say how the future may look like, because I think there are two opposite predictions, I would say. Some people say that we will still be getting better and better progress, and it's just a matter of time when we will have quantum computers which will achieve quantum supremacy. But it's important to know that there are also some obstacles on the road towards real quantum supremacy. For example, one of problems is the coherence. So our quantum system should be isolated from the environment. It's not easy, but we can do it, but it's not easy to keep the coherence for a long time. Also, it's difficult to prove that quantum algorithms will be better than classical algorithms, even for Shor's algorithm, right? I said that we only expect that there is no polynomial time algorithm on classical computers which can factor n-digit numbers, but it hasn't been proved. It's challenging to build some quantum gates. There is a problem with error correction because there is noise in computations, right? So that we may have different number of physical qubits and different number of logical qubits. So I will also tell about it in a second. I tell that it's difficult to prove that quantum algorithms will be better than classical. There is a quite famous case that one professor gave a task to one of his talented students to just prove that a given problem related to recommendation cannot be solved on classical computers in polynomial time, so that we have quantum supremacy in this case. But unfortunately, the student proved something opposite, right? So he found a polynomial algorithm to a problem which for many years was believed to be non-polynomial. But it also indicates that just working on quantum algorithms and quantum computers may also bring advantages, also in case of building classical algorithms, because this new classical algorithms was inspired by quantum algorithm. That's also interesting. I told about error correction. So the problem is that if we have noise, so for example, if we do measurement or we apply quantum gates, then the results of our computations may be a bit different than it should be. And in order to just get rid of it, we can just introduce some error corrections. So for example, we can, in the easiest setting, we can just represent one qubit, not as a one physical qubit, but as 3 physical qubits. So for example, we translate quantum state 0 to 3 zeros and quantum state 1 to 3 ones. And in that case, if we assume that we have at most one error, then we can still get the correct value, right? So it's possible to introduce an error correction. And now it's something very important, because in 90s of the 20th century, it was proved that such quantum error correcting codes exist, and these quantum error correcting codes could theoretically push error rates close to 0. And this was the central discovery that convinced people that scalable quantum computers should be possible at all, because before it was not sure. And Scott Arrowson, famous researcher working on quantum computers, said that now it's merely a staggering problem of engineering. And based on that, we believe that building larger and larger quantum computers will be possible, and in fact we can observe it, that the recent progress also indicates that we can overcome all obstacles. But some people also think that at some point it will just stop, and probably we will discover some new problems, and maybe also we'll also develop the theory of quantum mechanics thanks to that, because we still don't know everything about it. All right, but before we have such large quantum computers, we have to deal with a noise, and that's why there is so-called as noisy intermediate scale quantum approach. So we try to build algorithms assuming that there might be a noise, right? So we know that there might be a noise in computations, and we have to deal with it somehow, right? Okay, so there are several approaches to building quantum computers. I think that the most successful recently are based on superconducting qubits. So in case of gate-based computers, we can achieve the largest number of qubits, 72 qubits. In case of quantum annealing and adiabatic quantum computers, I already said that we have more than 2,000 qubits, and it's expected that next year we'll have 5,000. Just to give you an example, that's a sample code from the penny lane framework. So you can see that we can run code in Python, and then then run the code on a hybrid approach, partially on classical computer, partially on quantum computer, similarly as we do some machine learning experiments, then we run some computations on classical computers, but some on GPU, for example. QASM, so it's so similar to classical assembler. Qiskit is a programming framework from IBM. PyQL, it's a framework from Rigetti company. Project Q, another interesting project developed under development at the ETH Zurich. All right, so finally at the end I would like to share with you my experience with building quantum computing awareness and community in Poland. So I started working in this field in 2017. Initially I founded a Facebook group which is called Quantum AI, and now it has more than 900 members. And I expect that even this year will pass 1,000. And last year, in November, we started Warsaw Quantum Computing Group. So again, there is a Facebook group, and I invite you to join. We have more than 500 members. And we also have meetings. So we started this group in November 2018 to celebrate 100th anniversary of regaining independence by Poland. And later we organized 8 meetings so far. Our meetings are hosted in Przestrzeń from Facebook, or MIMU faculty, or Google Warsaw office. We also have a YouTube channel, so we record our meetings and make them publicly available on YouTube, so you can also subscribe and follow our channel. And as I said, we organize meetings with lectures and networking. We also organized this year the first in Warsaw workshop on programming quantum computers. It was in May. So our idea and our goal is to educate people in quantum computing, build awareness in this area. And we're also looking for scientists, enthusiasts, partners, persons to join this community. Beside that, we also recently established something that is called Q Poland. It's part of the Q World initiative. So we collaborate with similar groups in other countries. Right now we have 5 countries, but we hope that other countries will join us soon. So we prepare together educational materials, and we organize workshops in different cities. So it started this year by our colleagues from Riga, from Latvia. They just traveled to different cities in Europe and just gave workshops on programming quantum computers. One of them was in Warsaw. And we are keen to organize similar workshops also in other cities, so if someone here in Bydgoszcz is interested, just let me know and we can think about it. Beside that, I recommend you to learn from online courses. There is a MOOC, Massive Open Online Course on quantum machine learning. There are some interesting videos available on YouTube. I recommend you especially lectures of Peter Witek from University of Toronto, and also, of course, lectures from our meetings. There are some interesting Facebook groups to which you can join and also share information, learn from other people. There are many online tutorials, how to write program which can be run on Qiskit, PyQL, Penelame, etc. There are some conferences, but I think it's rather for a bit more, so for more advanced people who are already specialists in quantum technologies. One of meetings that will happen soon will be in Braga in Portugal in October this year. Also in October there will be the hackathon, quantum computing hackathon in CERN, 18 to 20 of October. It's still possible to register, so I encourage you to do that. And finally, I would also like to invite you to the next meeting of the Warsaw Quantum Computing Group, which we organize. It will be on 7th October in Google Warsaw office, and the lecture will be given by Professor Jacob Biamonte from Skolkovo Institute of Science and Technology. The title is Variational Quantum Machine Learning. We'll start the registration this Sunday, so please join and follow our Facebook group to be up to date. Thank you for your attention. If you have any questions, I'll be happy to answer them now or during the networking part. And I finally would also like to thank organizers for inviting me to be here. Thanks once again.